Right now, you are sitting on a rock hurtling through space at 670,000 miles per hour. That rock orbits a nuclear furnace 1 million times its size. That furnace is one of 400 billion stars spinning through a galaxy so vast that light itself needs 100,000 years to cross it. But here is what will shatter your mind. Our entire galaxy, with all its billions of worlds and countless civilizations that might exist, is nothing more than a single grain of sand in an ocean containing 2 trillion other grains. If you enjoy journeys that change how you see reality, hit that like button and subscribe. Prepare yourselves. We begin. Picture yourself standing in the middle of New York City at midnight. The lights stretch endlessly in every direction. Buildings fade into darkness at the horizon. Now imagine that cityscape extending not just to the next state, but across the entire continental United States. Then stretch it across the Pacific Ocean to Asia. Keep stretching it around the entire Earth. Then multiply that distance by 6 billion. You have just visualized the width of our galaxy. Scientists confirmed through precise measurements that the Milky Way spans 100,000 light-years from edge to edge. 1 light-year equals 6 trillion miles. This means our galactic home measures 600,000 trillion miles across. Writing out that number would require a line of zeros stretching from your house to the nearest grocery store. But here lies the first shock to human intuition. Despite this mind-crushing scale, our galaxy represents merely the first step in a cosmic ladder that climbs toward infinities our brains cannot process. Every single point of light you see twinkling in the night sky belongs to our galactic neighborhood. The fuzzy band of stars cutting across dark skies reveals the edge-on view of our spiral arms. We live inside this cosmic city, embedded within its structure like a single cell inside a massive organism. From our position, roughly 26,000 light-years from the galactic center, we can observe star formation regions where new suns ignite every year. We witness stellar nurseries where gravity sculpts gas clouds into burning spheres. Ancient red giants expire in spectacular explosions that seed space with heavy elements. All of this cosmic drama unfolds within our local galactic theater. Yet, what makes this scale truly disturbing is not its size, but what it represents. Our galaxy forms just one unit in a hierarchy of structures that grows increasingly vast and incomprehensible. Each level of cosmic organization dwarfs the previous one by factors that render human experience meaningless. Standing on Earth and contemplating galactic distances feels like an ant trying to comprehend the size of North America. The ant can sense that something vast exists beyond its immediate surroundings, but lacks the cognitive framework to grasp continental scales. Humans face the same limitation when confronting cosmic distances. Our evolved brains, designed for hunting on African plains, struggle with scales beyond our immediate environment. This cognitive barrier becomes our first hint that the universe operates on levels far beyond human intuition. Each cosmic structure we discover forces us to abandon our earthbound perspectives and embrace scales that feel more like mathematical abstractions than physical reality. The ancient Greeks believed the stars were holes poked in a celestial sphere surrounding Earth. Modern astronomy reveals that our galactic home alone contains mysteries that would have overwhelmed their wildest imagination. Every telescope that peers deeper into space discovers new layers of cosmic organization, stretching toward horizons we can barely detect. But compared to what comes next, our galaxy looks like a single room in a cosmic mansion, with countless floors extending toward infinity. Light moves faster than anything else in the universe. Nothing can outrun a photon racing through the vacuum of space. At 670 million miles per hour, light circumnavigates Earth 7 times in a single second. This cosmic speed limit represents the fastest possible way to traverse distances in our reality. Yet even light, the ultimate speedster of physics, requires 100,000 years to travel from one edge of our galaxy to the other. Think about what this means for human perspective. The light, leaving distant stars in our galaxy tonight, began its journey when early humans first learned to make fire. Photons, now reaching Earth from the far side of the Milky Way, started traveling before written language existed. These ancient light particles carry information about stellar events that occurred when our ancestors were still discovering agriculture. Scientists use this light travel time as a cosmic measuring stick. When astronomers observe distant galactic regions, they see them as they existed thousands of years ago. The galaxy we observe tonight is actually a patchwork of different time periods. Nearby stars show us recent events. Distant stellar neighborhoods reveal ancient history. We never see our galaxy as it exists right now, but rather as a time-averaged composite spanning millennia. This temporal displacement creates one of astronomy's strangest confirmed facts. Every photograph of our galaxy shows multiple time periods simultaneously. The light from various galactic regions left their sources at different historical moments. Looking at the Milky Way means looking backward through time across a span longer than human civilization. But this journey time becomes even more mind-bending when we consider galactic rotation. Our entire galaxy spins like a cosmic pinwheel. The solar system orbits the galactic center once every 200 million years. During light's journey across our galaxy, the entire structure completes nearly half a rotation. The galaxy literally changes shape while light travels between its regions. Even more disturbing is what this implies about cosmic communication. Any attempt to send signals across our galaxy faces this fundamental barrier. Radio waves and laser beams travel at light speed, meaning galactic communication requires patience measured in geological time. If an alien civilization on the far side of our galaxy sent us a message today, our great-great-grandchildren would need to wait for our great-great-grandchildren to receive it. This communication barrier means that our galaxy can never function as a unified system. Different regions operate independently, isolated by the fundamental speed limit of information transfer. What appears to be a single cosmic structure actually consists of countless independent zones, each evolving without knowledge of distant galactic neighborhoods. The ancient photons reaching us tonight carry messages from a galactic past we can observe but never revisit. Every star we see tells us about conditions that existed before our species learned to look up at the night sky. And yet this galactic communication challenge represents merely the smallest scale problem we face when trying to comprehend cosmic distances. Step outside on a clear night and locate the brightest star in the sky. That brilliant point of light is Sirius, burning 25 times brighter than our Sunday. It appears so luminous that ancient civilizations based their calendars on its movements. To your eyes, Sirius seems close enough to reach with a sufficiently tall ladder. The confirmed reality shatters this illusion completely. Sirius lies 8 and 6-10ths light years away from Earth. This distance equals 51 trillion miles. If you could drive a car at highway speeds toward this nearest bright star, the journey would require 300 million years. You would need to maintain 65 miles per hour continuously, since before complex life evolved on Earth. But Sirius is practically next door compared to typical galactic distances. Most stars in our galaxy are separated by gaps so vast they defy human comprehension. The average distance between neighboring stars measures 4 light-years. In cosmic terms, this represents an almost perfect vacuum, punctuated by occasional tiny islands of matter. To visualize this emptiness, imagine shrinking our solar system until the sun becomes the size of a basketball. At this scale, Earth would be a grain of sand orbiting 26 feet away. The nearest star would be another basketball located in a different city, perhaps Denver if you started in New York. Everything between these basketballs contains essentially nothing but empty space. This emptiness creates profound implications for space travel between stars. Even traveling at the speed of light, journeys to nearby stars require years. Conventional spacecraft moving at achievable speeds would need tens of thousands of years to reach the closest stellar neighbors. The vast majority of our galaxy remains forever inaccessible to human exploration. The void between stars also explains why alien contact seems so unlikely despite the enormous number of potential worlds. If alien civilizations exist on planets orbiting distant stars, they face the same fundamental barriers of space and time that isolate us. The universe conspires to keep intelligent species separated by gulfs too wide for meaningful interaction. Scientists have calculated that our galaxy contains roughly 400 billion stars, yet these countless suns are sprinkled so sparsely throughout galactic space that each one exists in splendid isolation. The night sky creates an optical illusion, making stars appear crowded together when they actually inhabit a realm of cosmic loneliness. This stellar isolation extends throughout our entire galactic neighborhood. Even the dense central regions of the Milky Way, where stars cluster more tightly than in our outer spiral arm, maintain vast, empty spaces between individual suns. The galaxy that appears so rich and populated in telescope images actually consists mostly of vacuum. Contemplating these vacant spaces between stars provides our first glimpse into the true nature of cosmic architecture. Matter represents rare exceptions scattered throughout an overwhelmingly empty universe. We inhabit tiny oases of substance floating in an ocean of nothingness. But this galactic emptiness looks positively crowded compared to the spaces that separate entire galaxies. Imagine counting every star in our galaxy. Begin with the Sun and work your way outward through the spiral arms. Count each red dwarf, each blue giant, each binary system spinning through space. Maintain a steady pace of 1 star per second without stopping to sleep or eat. You would finish counting after 12,600 years. Confirmed observations by space telescopes reveal that our galaxy contains between 100 billion and 400 billion stars. The exact number remains uncertain because dust clouds block our view of distant galactic regions. Dark nebulae hide stellar populations that we can detect only through infrared radiation. But even the conservative estimate of 100 billion stars overwhelms human comprehension. Each of these stellar furnaces burns with the power of nuclear fusion. Every second, our sun converts 4 million tons of matter into pure energy. Multiply this output by hundreds of billions of similar reactions occurring simultaneously throughout our galaxy. The total energy production of the Milky Way exceeds the power consumption of human civilization by factors that require scientific notation to express. Yet this staggering stellar population creates an unsettling realization. Despite containing enough suns to power quadrillions of civilizations, our entire galaxy represents a minuscule fraction of cosmic existence. Astronomers classify the Milky Way as a medium-sized spiral galaxy. Larger galaxies contain more than 1 trillion stars. Smaller dwarf galaxies harbor only a few billion stellar furnaces. The probability mathematics surrounding galactic star counts suggests mind-bending possibilities for planetary systems. If even 1% of galactic stars host Earth-like worlds, our galaxy contains billions of potentially habitable planets. Some of these worlds might harbor civilizations far older and more advanced than human society. Others might contain life forms so alien that we lack vocabulary to describe them. But what makes these numbers truly disturbing is their cosmic insignificance. Every star we have ever observed, every planet we might discover, every possible alien civilization that might exist within our galactic borders amounts to less than 1% of the matter in the observable universe. Our galaxy, with all its countless worlds, represents a single grain of sand on an infinite beach. This perspective shift challenges human-centered thinking about our cosmic importance. The ancient belief that Earth occupied the center of creation seems quaint compared to modern revelations about galactic scales. We exist on one planet, orbiting one star among hundreds of billions, in a galaxy that ranks as perfectly ordinary among trillions of similar structures. The 400 billion stars of our galaxy burn with energies that dwarf terrestrial phenomena. Their combined light output creates the glowing band we observe stretching across dark skies. Their gravitational interactions shape the spiral arms where new stars continue forming. Their life cycles seed space with heavy elements necessary for rocky planets and biological evolution. All of this cosmic grandeur unfolds within what amounts to our immediate galactic neighborhood. The next level of cosmic organization makes our entire stellar city look like a single house on an infinite street. Look toward the constellation Andromeda on any autumn night. That faint smudge of light appears unremarkable among the surrounding stars. Ancient astronomers catalogued it as a nebula, assuming it belonged to our local cosmic neighborhood. Modern telescopes reveal a truth that should terrify and inspire in equal measure. You are looking at another galaxy containing over 1 trillion stars. The Andromeda galaxy stretches 220,000 light-years across, making it more than twice the diameter of our Milky Way. This galactic giant harbors enough stellar furnaces to dwarf our local star count by factors of 3 or 4. If our galaxy is New York City, Andromeda represents the entire eastern seaboard of the United States. But confirmed measurements reveal something even more remarkable. Andromeda is racing toward us at 250,000 miles per hour. This cosmic collision course will culminate in the most spectacular event our solar system will ever witness. Computer simulations show that in 4.5 billion years, these two galactic titans will merge in a gravitational dance lasting several billion years. The collision will reshape both spiral structures into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. During this merger, our solar system will likely survive intact. The vast spaces between individual stars mean that stellar collisions remain extremely unlikely, even during galactic impacts. Instead, gravitational forces will fling our Sun and its planets into new orbits around the combined galactic center. Earth might end up in the outer regions of the merged galaxy, gazing upon unfamiliar constellations. Yet, what makes Andromeda truly mind-bending is not its size or approaching collision, but what it represents about cosmic distances. The light you see from Andromeda tonight began its journey 2.5 million years ago. When those photons started traveling toward Earth, early human ancestors were just learning to use stone tools. The galaxy you observe existed before modern humans evolved. This temporal displacement means we can never see Andromeda as it exists today. We observe its ancient past, preserved in light that has traveled across the cosmic void for millions of years. The galaxy approaching us right now might look completely different from what we observe through telescopes. Even more disturbing is what Andromeda reveals about cosmic scales. Despite being our nearest major galactic neighbor, it lies so far away that light requires millions of years to bridge the gap. This distance represents the smallest meaningful step beyond our local galactic environment. Between our galaxy and Andromeda stretches a void containing almost nothing but dark matter and scattered gas clouds. This intergalactic space harbors temperatures near absolute zero and densities lower than the best vacuum chambers humans can create. Yet, this seemingly empty gulf teems with invisible forces that govern galactic motions across cosmic time. The approaching merger of our galaxy with Andromeda will create fireworks visible from distant galactic neighborhoods. But even this cosmic spectacle represents merely a local event in a much larger gravitational theater. Our galaxy does not drift alone through cosmic space. The Milky Way belongs to a gravitational family called the Local Group, containing over 50 individual galaxies locked in an eternal cosmic dance. This galactic neighborhood spans roughly 10 million light-years and harbors enough combined mass to bend space and time across vast distances. Confirmed observations reveal that most galaxies in our local group are dwarf systems containing only a few billion stars each. These cosmic midgets orbit around the two dominant spiral galaxies, our Milky Way and the approaching Andromeda. Like planets circling a binary star system, these smaller galaxies follow complex orbital paths determined by the gravitational interplay between the two largest group members. The most prominent dwarf companions are the Large and Small Magellanic Clouds, visible to naked eye observers in the southern hemisphere. These irregular galaxies orbit our Milky Way at distances of 160,000 and 200,000 light-years respectively. Their proximity makes them laboratories for studying galactic interactions in real time. Scientists have discovered that our galaxy is actively cannibalizing its smaller neighbors. Tidal forces created by the Milky Way's immense gravitational field strip stars and gas from the Magellanic Clouds, feeding material into our galactic disk. This cosmic feeding process has continued for billions of years, with our galaxy growing larger by consuming nearby dwarf systems. But this galactic predation reveals something profound about cosmic evolution. Galaxies do not exist as isolated islands floating through empty space. They inhabit gravitational communities where constant interactions shape their structure and evolution. The peaceful appearance of night sky, galaxies, masks, violent processes that unfold over cosmic timescales. The local group itself moves through space as a coherent unit. Our entire galactic neighborhood travels toward the Virgo cluster at roughly 400 miles per second. This motion carries our local collection of galaxies across distances that dwarf individual galactic sizes. We are passengers on a cosmic vessel sailing through intergalactic space toward gravitational destinations we can barely perceive. Even more remarkable, the galaxies within our local group are bound together by dark matter halos that extend far beyond their visible edges. These invisible gravitational scaffolds contain 10 times more mass than all the stars and gas we can observe. Dark matter provides the gravitational glue that holds galactic groups together despite the expansion of space itself. The orbital dynamics within our local group follow precise mathematical laws that govern motion across cosmic scales. Each galaxy traces elliptical paths through space, periodically approaching and receding from its neighbors in cycles lasting billions of years. These gravitational interactions trigger star formation, distort galactic shapes, and redistribute matter across vast distances. Understanding our galactic neighborhood requires thinking in timescales that exceed human experience. The current configuration of the local group represents just one moment in a cosmic evolution spanning tens of billions of years. Galaxies merge, separate, and merge again in patterns too slow for human observation, but recorded in the motions we measure today. This local gravitational dance represents merely the smallest organizational unit in a cosmic hierarchy that grows increasingly complex. Galaxy clusters represent the most massive gravitationally bound structures in the universe. These cosmic cities contain thousands of individual galaxies held together by forces so powerful they distort space and time across millions of light years. The nearest major cluster, called Virgo, contains over 1,300 galaxies and lies 54 million light-years from our local group. Confirmed measurements reveal that galaxy clusters should not exist according to the visible matter we observe. The combined gravitational pull of all stars and gas in cluster galaxies cannot account for the tremendous forces needed to hold these structures together. Galaxies within clusters move at speeds approaching 3 million miles per hour. Such velocities should have scattered cluster members across cosmic space billions of years ago. The solution to this puzzle required discovering that most cluster mass remains completely invisible. Dark matter outweighs visible stars and gas by ratios of 10:1 throughout galaxy clusters. This mysterious substance reveals itself only through gravitational effects on light and matter, creating a cosmic scaffolding we can map but cannot directly observe. Scientists use gravitational lensing to study dark matter distribution in galaxy clusters. Massive clusters bend space so severely that they act like cosmic magnifying glasses, distorting the appearance of background galaxies. The amount of distortion reveals how much invisible mass clusters contain. These measurements confirm that dark matter dominates cluster structure, despite remaining undetectable to any instrument humans have built. The most spectacular example of dark matter evidence comes from the Bullet Cluster, where two galaxy clusters collided at speeds exceeding 10 million miles per hour. During this cosmic collision, the visible gas clouds interacted and slowed down, but the dark matter components passed through each other unchanged. Gravitational lensing maps show dark matter and visible matter separated by millions of light years, providing direct proof that invisible mass exists independently of stars and gas. Galaxy clusters also serve as cosmic laboratories for studying extreme physics. The hot gas between cluster galaxies reaches temperatures of 100 million degrees, hot enough to strip electrons from atoms and create plasma that glows in X-ray wavelengths. This superheated material contains more mass than all the cluster galaxies combined, yet remains invisible to optical telescopes. The space between cluster galaxies teems with high-energy particles accelerated to near light speed by magnetic fields spanning millions of light years. These cosmic ray particles create radio emissions detectable by specialized telescopes, revealing magnetic structures that connect distant galaxies within clusters. But what makes galaxy clusters truly mind-bending is their role in cosmic evolution. Clusters represent the endpoints of gravitational collapse in our universe. Dark matter began clumping together shortly after the Big Bang, eventually creating the gravitational wells where galaxies formed. Over cosmic time, these galactic collections merged into increasingly massive clusters. The largest known galaxy cluster, called El Gordo, contains the mass of 3 quadrillion suns and spans 15 million light-years. This cosmic monster lies 7 billion light-years away, meaning we observe it as it existed when our solar system was just forming. Galaxy clusters form nodes in an even larger cosmic structure that resembles a 3-dimensional spiderweb. Superclusters represent the largest confirmed gravitational structures in our universe. These cosmic formations stretch across distances so vast that light requires hundreds of millions of years to traverse them. Our local group belongs to the Laniakea supercluster, a gravitational collection spanning 500 million light-years and containing over 100,000 galaxies. The discovery of superclusters revolutionized our understanding of cosmic organization. Instead of being randomly scattered through space, galaxies arrange themselves in vast networks, connected by filaments of dark matter and gas. These cosmic highways channel matter across distances that dwarf individual galaxy clusters, creating a hierarchical structure that extends to the largest observable scales. Scientists mapped our local supercluster by tracking the peculiar motions of thousands of galaxies. Despite cosmic expansion pushing distant galaxies apart, gravity causes nearby galaxies to move toward regions of higher density. By measuring these gravitational flows, astronomers revealed that our Milky Way and millions of neighboring galaxies are all streaming toward a massive gravitational attractor. This attractor, called the Great Attractor, contains the combined mass of tens of thousands of galaxies concentrated in a region obscured by dust clouds in our galactic plane. The gravitational pull from this cosmic monster influences galaxy motions across hundreds of millions of light-years, creating currents in the cosmic web that carry entire galaxy clusters toward areas of increasing density. But the Great Attractor itself represents only a small component of an even larger structure. Recent observations reveal that Laniakea forms part of an enormous complex of superclusters spanning more than 1 billion light-years. This structure, called the Pisces Cetus supercluster complex, may represent the largest coherent structure in the observable universe. The implications of supercluster organization challenge our understanding of cosmic evolution. These vast structures formed through gravitational processes that required billions of years to create the patterns we observe today. Dark matter began clumping together when the universe was less than 1% of its current age, eventually creating the scaffolding along which visible matter organized itself. Supercluster boundaries remain difficult to define precisely because they blend into neighboring structures. Unlike galaxy clusters, which are clearly bound by gravity, superclusters represent looser associations that may be dispersing due to cosmic expansion. Some regions within superclusters continue collapsing under their own gravity, while other areas are being stretched apart by dark energy. The shape of superclusters resembles biological structures more than geometric objects. Laniakea looks like a vast sheet with tendrils extending in multiple directions, similar to neural networks in the human brain. This resemblance may not be coincidental, as both systems organize through processes that create branching, hierarchical structures. Observing supercluster structure requires telescopes capable of mapping millions of galaxies across vast distances. The Sloan Digital Sky Survey created three-dimensional maps, revealing supercluster organization by measuring precise distances to over 1 million galaxies. These surveys show that superclusters connect to form even larger structures resembling cosmic scaffolding. The cosmic web that emerges from supercluster mapping looks like soap bubbles floating in space, with galaxies concentrated along bubble edges and enormous voids occupying bubble interiors. This soap bubble architecture extends throughout the observable universe. Step back far enough from the universe, and a stunning pattern emerges. Galaxies do not scatter randomly through space, but organize themselves into a vast three-dimensional network, resembling soap foam floating in cosmic darkness. This structure, called the cosmic web, represents the largest scale organization of matter in our universe. Computer simulations confirm that this web-like architecture formed naturally through gravitational processes beginning shortly after the Big Bang. Dark matter started clumping together when the universe was only a few 100,000 years old, creating gravitational seeds that eventually grew into the cosmic scaffolding we observe today. The cosmic web consists of 4 distinct components, working together across billions of light years. Dense nodes mark the intersections where galaxy clusters form. Filaments stretch between nodes like cosmic highways, channeling matter across vast distances. Walls form sheet-like structures where filaments intersect. Between these structures lie cosmic voids containing almost nothing but empty space. Scientists have mapped this cosmic architecture by observing millions of galaxies and measuring their three-dimensional positions in space. The resulting surveys reveal that galaxies trace out the edges of enormous bubbles, with void regions occupying bubble interiors. This foam-like structure extends throughout the observable universe with remarkable consistency. The scale of cosmic web components defies human intuition. Individual filaments stretch across hundreds of millions of light-years while maintaining widths of only 20 million light-years. These cosmic threads appear impossibly thin when viewed at universal scales, yet they contain enough matter to fuel billions of galaxies. Matter flows along filaments like water through cosmic plumbing, feeding galaxy formation in the densest regions. Galaxy clusters form where multiple filaments intersect, creating gravitational traffic jams that trap matter for billions of years. These cosmic crossroads represent the busiest neighborhoods in the universe, where galaxy interactions trigger star formation and supermassive black hole growth. The most massive clusters mark the locations where the cosmic web reaches its highest density. But what makes the cosmic web truly remarkable is its dynamic nature. This structure continues evolving as cosmic expansion stretches the universe and dark energy accelerates the separation between distant regions. Filaments that currently connect distant superclusters will eventually snap as space expands beyond the reach of gravitational forces. The gas threading through cosmic web filaments remains mostly invisible to optical telescopes, but glows faintly in ultraviolet and X-ray wavelengths. This intergalactic medium contains more mass than all the stars in the universe combined, yet it spreads so thinly that cubic meters of this material contain only a few atoms. Recent observations have detected the warm-hot intergalactic medium predicted to fill cosmic web filaments. This material reaches temperatures of millions of degrees while maintaining densities barely above the cosmic vacuum. Finding this elusive component required specialized X-ray telescopes capable of detecting extremely faint emissions from hot gas. The cosmic web extends beyond our current observational capabilities, suggesting that the structures we can map represent only a small fraction of universal organization. Hidden within this web lie cosmic voids so empty they challenge our understanding of space itself. Imagine a sphere of space 300 million light-years across, containing almost nothing. No galaxies shine within this cosmic desert. No stars illuminate its darkness. No planets orbit through its void. This empty realm, called a cosmic void, represents one of the most mysterious regions in our universe. The Boötes void, discovered in 1977, spans 330 million light-years in diameter, while containing fewer than 60 known galaxies. If our local group existed within this cosmic bubble, the nearest major galaxy would lie so far away that it would appear as a barely detectable smudge in our most powerful telescopes. Confirmed observations reveal that cosmic voids occupy roughly 80% of universal volume. These enormous empty regions separate the cosmic web filaments where galaxies cluster together. Despite their vast size, voids contain less than 15% of the average matter density found elsewhere in the universe. Scientists initially struggled to explain how such empty regions could exist. Early theories suggested that voids formed through explosive events that cleared matter from huge volumes of space. Modern research reveals that voids represent natural consequences of cosmic web formation. As matter clumped together along filaments and walls, it drained away from the regions that became voids. The emptiness within cosmic voids creates conditions unlike anywhere else in the observable universe. Temperatures inside voids hover just a few degrees above absolute zero. Densities fall so low that individual hydrogen atoms may be separated by distances measured in miles rather than microscopic scales. These conditions approach the perfect vacuum that physicists can create only in specialized laboratory chambers. Yet voids are not completely empty. They contain invisible dark matter that forms the gravitational framework connecting them to surrounding structures. Computer simulations show that void regions contain dark matter filaments, too tenuous to gravitationally trap normal matter. These invisible threads create a web within the web, extending cosmic organization into apparently empty space. Galaxies that do exist within voids follow different evolutionary paths than their counterparts in denser regions. Void galaxies tend to be smaller, bluer, and more actively forming stars than typical galaxies. The isolation within voids protects these rare galaxies from gravitational interactions that would disrupt their star formation processes. The largest known void, called the Giant Void or Canes Venaticus supervoid, spans 1.8 billion light-years across. This cosmic desert contains so little matter that if our Milky Way existed at its center, we would not have discovered the existence of other galaxies until the 1960s. The night sky would appear almost completely dark, except for our local galactic neighbors. Cosmic voids also affect the cosmic microwave background radiation left over from the Big Bang. Photons passing through void regions experience slightly different gravitational effects than those traveling through denser areas. These subtle temperature variations provide another way to map void locations across cosmic distances. The expansion of space preferentially affects void regions, causing them to grow larger over time, while matter continues draining towards surrounding structures. But even these enormous empty regions look small compared to the largest solid structures astronomers have discovered. The largest solid structures in the observable universe stretch across distances so vast they challenge the fundamental limits of what cosmic physics should allow. These enormous walls and sheets of galaxies span billions of light-years, while maintaining thicknesses of only 20 million light-years, creating cosmic architecture that resembles impossibly thin membranes floating through space. The first galactic wall discovered by astronomers, called the Coma Wall, extends 500 million light-years in length, while measuring only 16 million light-years thick. This cosmic structure contains thousands of galaxies arranged in a thin sheet that would appear edge-on as a barely visible line if viewed from the side. The wall lies 300 million light-years from our local group, making it a prominent feature in our cosmic neighborhood. But confirmed observations have revealed far larger structures that push the boundaries of theoretical predictions. The Sloan Great Wall spans 1.3 billion light-years across, making it one of the largest known structures in the universe. This cosmic barrier contains hundreds of thousands of galaxies, organized into a coherent pattern that extends across roughly 1% of the observable universe diameter. Even more remarkable is the Hercules Corona Borealis Great Wall, discovered through mapping gamma-ray bursts from distant galaxies. This structure measures 10 billion light-years across, making it so large that light requires more than 1/10 of the universe's age to travel from one end to the other. The existence of such enormous structures challenges theoretical models of how cosmic organization should develop. These galactic walls form where cosmic web filaments intersect across vast distances. Computer simulations show that dark matter naturally creates sheet-like structures when gravitational forces pull matter together from multiple directions simultaneously. Normal matter follows these dark matter scaffolds, creating the galaxy concentrations we observe. The thinness of cosmic walls creates gravitational effects that influence galaxy evolution across enormous distances. Galaxies within walls experience enhanced tidal forces that can trigger star formation bursts or strip matter from smaller neighboring systems. The gravitational environment within walls differs significantly from conditions in cosmic voids or dense cluster cores. Scientists use cosmic walls as laboratories for studying large-scale structure formation. The precise arrangement of galaxies within walls provides clues about the initial conditions that existed shortly after the Big Bang. Comparing observed wall structures with computer simulations helps test theories about dark matter properties and cosmic evolution. But what makes these walls truly mind-bending is their role in universal organization. Despite their enormous size, cosmic walls represent intermediate-scale structures between superclusters and the largest detectable patterns in galaxy distribution. They form components of even larger organizational schemes that extend toward the limits of observational capability. The discovery of cosmic walls also reveals the dynamic nature of large-scale structure. These enormous features continue evolving as cosmic expansion stretches the universe. Walls that appear solid today will eventually fragment as dark energy overcomes gravitational forces, holding their components together. Some cosmic walls may extend beyond our current observational horizon, connecting to structures we cannot yet detect. This possibility hints at organizational patterns spanning the entire observable universe. Point the most powerful telescope ever built toward any tiny patch of apparently empty sky. Keep the camera open for days, collecting every photon that arrives from that cosmic direction. The resulting image will reveal something that should fundamentally change how you think about existence. That tiny region, no larger than a grain of sand held at arm's length, contains thousands of galaxies. The Hubble Ultra Deep Field created by combining 800 separate images with 11 days of total exposure time, revealed over 10,000 galaxies in a patch of sky covering just 1/13 millionth of the celestial sphere. Each galaxy in this cosmic census contains billions of stars, many likely hosting planetary systems where life might exist. Confirmed analysis of deep field observations allows astronomers to calculate the total galaxy population within our observable universe. The most recent estimates, based on data from the Hubble and James Webb Space Telescopes, suggest that 2 trillion galaxies populate the cosmic volume we can currently detect. 2 trillion represents a number that overwhelms human comprehension. If you could observe one galaxy per second without stopping, you would need 63,000 years to see them all. Written out completely, this number requires 13 zeros, 2 million galaxies scattered throughout observable space. Each of these galactic islands contains its own stellar populations. Conservative estimates suggest that the average galaxy harbors 100 billion stars. Multiplying galaxy count by stellar populations yields a cosmic census exceeding 10 to the 24th power individual stars. This number surpasses the count of grains of sand on every beach on Earth. But what makes this galactic abundance truly disturbing is how it redistributes significance in the cosmic hierarchy. Our entire local group, containing over 50 galaxies, represents less than 1/50 billionth of the total galactic population. The Milky Way, with its 400 billion stars, ranks as utterly typical among the 2 trillion cosmic neighbors sharing our universe. Recent observations suggest that galaxy counts may actually underestimate universal populations. Improved detection techniques continue discovering faint dwarf galaxies that previous surveys missed. These tiny galactic systems, containing only millions of stars each, may outnumber large spiral galaxies by ratios of 10 to 1. Deep field observations also reveal galaxies at various stages of cosmic evolution. Distant galaxies appear as they existed billions of years ago, when the universe was young and star formation rates exceeded current levels. These ancient systems show different structures and compositions than nearby modern galaxies, providing glimpses into cosmic history. The distribution of galaxies throughout space follows the cosmic web pattern, extending to the largest observable scales. Galaxy counts remain roughly constant in all directions astronomers look, confirming that universal structure appears uniform when viewed from cosmic distances. This uniformity suggests that our observable volume represents a fair sample of universal contents. Yet, every galaxy survey pushes deeper into space, reveals additional cosmic neighbors previously hidden beyond detection limits. Each improvement in telescope sensitivity adds billions of galaxies to the cosmic census. The 2 trillion galaxies we can currently detect may represent only a small fraction of total galactic populations. Walk along any ocean shoreline and scoop up a handful of sand. Count the individual grains between your fingers. A typical handful contains roughly 10,000 tiny fragments of rock and shell, each grain representing millions of years of erosion and weathering. Now expand your count to encompass every beach on Earth. Include the Caribbean islands, the Mediterranean coast, the Pacific atolls, and the Arctic shores. Count every grain of sand on every beach, surrounding every continent and every island on our planet. Scientists estimate that Earth's beaches contain approximately 7 quintillion grains of sand. Written with zeros, this number spans 20 digits, 7 million individual particles. This astronomical count of earthly sand grains pales in comparison to cosmic stellar populations. Confirmed observations reveal that the observable universe contains more stars than grains of sand on Earth. The 2 trillion galaxies we can detect harbor enough stellar furnaces to dwarf our planetary sand count by factors of thousands. Every time you pick up a handful of beach sand, remember that cosmic space contains thousands of stars for each grain between your fingers. But this comparison becomes even more staggering when we consider planetary populations. Modern exoplanet surveys suggest that most stars host at least one planet, with many systems containing multiple worlds. If conservative estimates prove correct, the observable universe contains more planets than sand grains on Earth, multiplied by Earth's total number of atoms. Each of these countless worlds represents a unique experiment in planetary evolution. Rocky planets orbit in zones where liquid water could exist. Gas giants dominate outer planetary regions. Ice worlds harbor subsurface oceans. Desert planets bake under intense stellar radiation. The variety of planetary environments exceeds anything science fiction has imagined. The probability mathematics surrounding these numbers suggest mind-bending implications for life in the universe. Even if life emerges on just one planet per million suitable worlds, the cosmos should teem with biological activity. Some civilizations might have evolved billions of years before Earth formed. Others might possess technologies that make human achievements look primitive. Yet the vast distances separating star systems create isolation that prevents most worlds from ever communicating with their cosmic neighbors. The speed of light barrier ensures that civilizations separated by thousands of light years can never establish meaningful contact. Each inhabited world develops in cosmic solitude, unaware of the countless other experiments in intelligence occurring throughout the universe. This isolation explains why our night sky appears so quiet despite the enormous number of potential cosmic neighbors. Radio signals from alien civilizations would require centuries or millennia to cross the spaces between star systems. By the time messages arrive, the civilizations that sent them might have evolved beyond recognition or vanished entirely. The stellar census also reveals something profound about cosmic perspective. Every human who has ever lived exists on one planet, orbiting one star among more stellar furnaces than sand grains on Earth. Yet this incredible stellar abundance represents just the beginning of cosmic scales that dwarf even these mind-numbing numbers. The universe you can see tonight has boundaries, not physical walls marking the end of space, but fundamental limits imposed by the speed of light and the age of cosmic time. These boundaries define what astronomers call the observable universe, a sphere of space containing everything we can potentially detect using any technology humans might ever develop. Confirmed measurements reveal that this observable sphere measures 93 billion light-years in diameter. This distance represents the maximum extent of space from which light has had time to reach Earth since the universe began. Beyond this cosmic horizon lies a realm forever hidden from human observation. The calculation behind this cosmic boundary requires understanding both light, travel time, and cosmic expansion. Light from the most distant observable objects began its journey 13.8 billion years ago, when the universe was only 380,000 years old. But during the journey time, cosmic expansion stretched the space between source and destination. Objects that emitted light 13.8 billion years ago now lie 46.5 billion light-years away due to this cosmic stretching. Light that left distant galaxies when they were relatively nearby arrives at Earth after those same galaxies have been carried to much greater distances by expanding space. This creates one of the most counterintuitive facts about cosmic observation. The most distant galaxies we can see appear as they existed when the universe was young and small. Yet those same galaxies currently exist far beyond our observational horizon, evolved into forms we can never observe directly. The edge of the observable universe coincides with the cosmic microwave background radiation, the afterglow from when atoms first formed and space became transparent to light. This radiation provides a baby picture of the universe taken when it was less than 1% of its current age. But what makes the observable horizon truly mind-bending is its personal nature. Every observer in the universe has their own unique observable sphere centered on their location. Alien astronomers in distant galaxies observe cosmic volumes that overlap with ours. In some regions, while extending into space we can never see. The observable universe continues growing larger every day as light from increasingly distant regions reaches Earth for the first time. Each second, our cosmic visibility increases by 1 light second in every direction. Over cosmic time, this gradual expansion of observational range reveals new galaxies emerging from beyond the cosmic horizon. Yet this growing visibility cannot continue forever. Cosmic expansion will eventually overcome light travel, causing distant galaxies to cross permanently beyond our observational reach. The observable universe will begin shrinking as expansion carries cosmic neighbors across the cosmic horizon, never to be seen again. Current observations suggest that we live during a golden age of cosmic visibility. The observable universe currently contains more galaxies than at any previous time in cosmic history, yet fewer than will be visible in the far future when expansion isolates us from increasingly distant neighbors. This cosmic boundary raises profound questions about the nature of space beyond our observational limits. The universe we cannot see may be vastly larger than the cosmic volume available to human observation. Space itself moves faster than light. This statement appears to violate Einstein's cosmic speed limit, yet confirmed observations prove that the fabric of spacetime expands at rates that dwarf the velocity of photons, racing through the cosmic void. Einstein's relativity prohibits matter and energy from traveling faster than light through space, but space itself faces no such restriction. The universe can stretch its own fabric at any rate without violating physical laws. During cosmic inflation, space expanded so rapidly that regions separated by subatomic distances grew to cosmic scales in less than a second. This distinction between motion through space and expansion of space creates mind-bending consequences for cosmic observation. Galaxies at the edge of our observable universe are currently racing away from us at speeds approaching 3 times the speed of light. Yet these same galaxies are not actually moving through space at relativistic velocities. Instead, expanding space carries distant galaxies along like passengers on a cosmic escalator. The galaxies themselves maintain relatively modest speeds through local space, but the cumulative effect of expansion across billions of light-years creates apparent recession velocities that exceed light speed. Hubble's law quantifies this cosmic expansion through a simple relationship between distance and recession velocity. Galaxies twice as far away recede twice as fast. 3 times the distance means 3 times the speed. This linear relationship continues until recession velocities surpass the speed of light at distances exceeding 14 billion light-years. The discovery of accelerating cosmic expansion won the 2011 Nobel Prize in Physics. Observations of distant supernovae revealed that expansion rates are increasing over time rather than slowing down as astronomers expected. Dark energy, comprising 68% of universal contents, drives this accelerating expansion against gravitational forces. Current expansion rates suggest that space doubles in size every 10 billion years. This may seem slow compared to human timescales, but cosmic expansion operates across such vast distances that its effects accumulate to tremendous velocities at large scales. The acceleration of cosmic expansion means that most galaxies we can currently observe will eventually disappear beyond our cosmic horizon. In approximately 2 trillion years, only galaxies within our local group will remain visible to future astronomers. The night sky will appear almost empty except for our galactic neighbors, but expansion rates may continue increasing until dark energy overwhelms all other forces in the universe. Theoretical models suggest that accelerating expansion could eventually tear apart galaxies, star systems, and even atomic nuclei in an event called the Big Rip. This cosmic destruction would occur approximately 22 billion years from now. Yet the current expansion rate creates opportunities as well as isolation. Space telescopes can observe galaxies at distances where recession velocities approach light speed. These observations provide glimpses into cosmic conditions when the universe was young and stellar formation rates exceeded current levels. The expanding universe also allows astronomers to see farther back in time by observing increasingly distant objects. Each improvement in telescope sensitivity reveals earlier cosmic epochs, but expansion carries most of the universe beyond our permanent observational reach. The space we cannot see may extend infinitely in all directions. At the very edge of observable space glows a wall of ancient light, marking the boundary between visible cosmos and unknowable void. This cosmic microwave background radiation represents the oldest light in the universe, emitted when atoms first formed and space became transparent 13.8 billion years ago. Before this moment, called recombination, the universe contained too much free energy for stable atoms to exist. Protons and electrons remained separated in a cosmic soup so dense that light could travel only microscopic distances before scattering off charged particles. The universe was literally opaque, like being inside a glowing fog so thick that nothing could be seen beyond arm's length. When cosmic expansion cooled temperatures below 3,000 degrees, protons and electrons combined into hydrogen atoms for the first time. This removed the charged particles that scattered light, allowing photons to travel freely through space. The universe became transparent in a cosmic instant, releasing radiation that continues traveling toward us today. Confirmed observations detect this background radiation arriving from every direction in space with remarkable uniformity. Advanced satellites measure temperature variations of only a few millionths of a degree across the cosmic microwave background. These tiny fluctuations represent quantum uncertainties from the universe's birth, amplified by cosmic expansion into the seeds that eventually became galaxies. The cosmic microwave background serves as humanity's baby picture of the universe. We observe this radiation as it existed when cosmic time measured only 380,000 years, compared to the current age of 13.8 billion years. The patterns frozen in this ancient light reveal conditions when the first atoms formed and cosmic structure began emerging from primordial smoothness. But this radiation wall also marks the absolute limit of electromagnetic observation. No telescope can see beyond the cosmic microwave background because no light existed in observable form before recombination occurred. Earlier cosmic epochs remain hidden behind this wall of ancient radiation, accessible only through indirect detection of gravitational waves or neutrino emissions. The cosmic microwave background surrounds Earth like the inner surface of an enormous sphere centered on our location. Every point on this sphere lies exactly 46.5 billion light-years away, representing the maximum distance from which light has had time to reach us since the universe became transparent. Yet this observational boundary moves outward every day as cosmic expansion carries the background radiation source to greater distances. The sphere of cosmic microwave background emission grows larger continuously, but the radiation itself grows fainter and cooler as expansion stretches its wavelengths toward longer, less energetic frequencies. In the far future, cosmic expansion will stretch this background radiation beyond the detection capabilities of any conceivable instrument. The cosmic microwave background will fade into undetectable whispers, removing even this ancient signpost marking the edge of observable space. This radiation boundary raises profound questions about cosmic contents beyond our observational reach. The universe certainly existed before recombination occurred, but conditions during earlier epochs remain largely theoretical. Whatever lies beyond the cosmic microwave background wall may dwarf our observable universe in ways we cannot imagine. Beyond the cosmic microwave background lies a universe we can never see but know must exist. This hidden realm extends backward through cosmic time to periods when temperatures exceeded nuclear fusion cores, and forward through space to distances that may continue infinitely in all directions. Theoretical physics provides glimpses into cosmic conditions before the universe became transparent. During the first 380,000 years, temperatures exceeded those found in stellar interiors. Matter existed as plasma so hot that atomic nuclei could not hold onto electrons. The entire universe glowed brighter than the surface of any star. Even earlier epochs pushed physics to its theoretical limits. During the first 3 minutes after the Big Bang, cosmic temperatures allowed nuclear fusion to occur throughout space. Protons and neutrons combined into light elements, creating the cosmic abundance of hydrogen and helium we observe today. This primordial nucleosynthesis occurred when the universe was smaller than our solar system, yet contained all the matter we can currently observe. The first second of cosmic time remains largely mysterious. Theoretical models suggest that fundamental forces separated during this period as expansion cooled the universe, below energy scales, where particle physics breaks down. Gravity separated first, followed by the strong nuclear force, then electromagnetic and weak nuclear forces. But confirmed observations suggest that our universe extends far beyond the cosmic microwave background in spatial dimensions as well as temporal history. The flatness and uniformity of space indicate that cosmic inflation expanded the universe by enormous factors during its first tiny fraction of a second. This expansion stretched quantum fluctuations to cosmic scales while creating space much larger than our observable volume. If inflation theories prove correct, our observable universe represents an infinitesimally small portion of total cosmic volume. The region that became our observable sphere was smaller than a proton before inflation began. Expansion increased its size by factors exceeding 10 to the 26th power. Yet this inflated volume still constitutes only a tiny bubble within a vastly larger cosmic structure. Current models suggest that different regions of this larger universe may have evolved under different physical conditions. Areas beyond our cosmic horizon might have experienced different inflation rates, creating domains where physical constants take different values. Electrons might have different masses. Light might travel at different speeds. Gravity might operate with different strengths. These variations could create cosmic regions where stars form differently, where chemistry follows alternative rules, where life develops through unimaginable processes. Each domain might represent a unique experiment in physics, isolated from neighboring regions by expansion too rapid for communication. Some theoretical models propose that cosmic inflation continues in regions beyond our observable volume. New space constantly forms through eternal inflation, creating infinite numbers of observable universe-sized bubbles within an ever-growing cosmic structure. This possibility suggests that our observable universe, containing 2 trillion galaxies and more stars than grains of sand on Earth, represents merely one small chamber in an infinite cosmic mansion. The true scale of existence may extend far beyond human comprehension or observational capability. Scientists using advanced statistical analysis have calculated that our observable universe may represent less than 1% of total cosmic volume. Bayesian mathematical models suggest the true universe extends at least 250 times farther than the cosmic horizon we can detect, making the hidden cosmos vastly larger than anything humans will ever observe. This calculation relies on measuring the curvature of space across the largest observable scales. If the universe was smaller than our observable volume, space would show detectable curvature, like the surface of a sphere. But precise measurements of the cosmic microwave background reveal that space appears perfectly flat across billions of light years. Flat geometry indicates that the universe extends far beyond our observational limits. The region we can see represents a tiny patch within a cosmic structure so large that its curvature remains undetectable across distances spanning our entire observable sphere. This resembles standing on Earth's surface, where the ground appears flat because our planet is much larger than our local horizon. Conservative estimates based on cosmic flatness suggest the universe measures at least 7 trillion light-years in diameter. This minimum size exceeds our observable universe by factors of 75, meaning that for every galaxy we can detect, at least 5,000 similar galaxies exist beyond our cosmic horizon. But theoretical models propose even larger possibilities. Eternal inflation theory suggests that new space constantly forms through quantum processes, creating infinite numbers of observable universe-sized regions within an ever-expanding cosmic structure. Each region would contain its own collection of galaxies, stars, and planets, isolated from neighboring domains by expansion too rapid for light to bridge. This hidden cosmos raises profound questions about cosmic uniqueness. If the universe extends far beyond our observation, then conditions similar to those in our cosmic neighborhood must be repeated countless times throughout the larger structure. Planets identical to Earth might exist in distant cosmic domains. Civilizations equivalent to human society might develop around similar stellar systems. The probability mathematics surrounding an infinite universe suggests that every possible arrangement of matter must occur somewhere within the hidden cosmic volume. This includes not just Earth-like worlds, but perfect duplicates of our entire observable universe, repeated throughout infinite space. Yet this vast hidden realm remains forever inaccessible to human observation or exploration. Even traveling at light speed, explorers could never reach regions beyond our cosmic horizon because expansion carries them away faster than any signal can propagate. The hidden universe represents a realm we can theorize about but never directly study. Recent observations of cosmic microwave background polarization provide indirect evidence for the larger cosmic structure. Patterns in ancient light suggest that our observable region connected to neighboring domains during cosmic inflation. These connections left subtle imprints that surveil advanced instruments can detect. The discovery that our observable universe represents a tiny fraction of cosmic totality fundamentally changes our perspective on human significance. Every star we can see, every galaxy we can observe, every possible alien civilization within our cosmic horizon exists within less than 1% of universal content. The remaining 99% of existence lies forever beyond human knowledge. Something invisible is tearing the universe apart. Dark energy, comprising 68% of cosmic contents, accelerates the expansion of space with a force so powerful that it overwhelms gravity across distances larger than galaxy clusters. This mysterious component of reality pushes distant galaxies away from us at ever-increasing speeds. The discovery of cosmic acceleration shocked astronomers who expected gravitational forces to gradually slow universal expansion. Two independent research teams studying distant supernovae in 1998 found that cosmic expansion was speeding up rather than slowing down. This observation earned the 2011 Nobel Prize in Physics and revolutionized our understanding of cosmic evolution. Dark energy behaves unlike any known form of matter or radiation. While normal matter becomes less dense as space expands, dark energy maintains constant density throughout cosmic growth. This means that dark energy's influence grows stronger over time as space increases in volume, while dark energy density remains unchanged. Current expansion rates indicate that space doubles in size every 10 billion years. This may seem gradual, but dark energy's constant density means that its gravitational repulsion doubles every time space doubles. Cosmic acceleration, therefore, increases exponentially, creating runaway expansion that will eventually overcome all other forces in the universe. Confirmed observations show that dark energy currently dominates cosmic dynamics at scales larger than several hundred million light-years. Within this distance, gravitational attraction between matter concentrations can overcome dark energy repulsion. Beyond this scale, dark energy wins every gravitational battle, pushing cosmic structures apart despite their mutual attraction. This cosmic tug-of-war determines the fate of every galaxy we can observe. Galaxies within our local group remain gravitationally bound despite cosmic expansion, but galaxies in distant clusters are being carried away by dark energy at speeds that will eventually exceed light velocity. Most cosmic neighbors will disappear beyond our observational horizon within 2 trillion years. The nature of dark energy remains one of the greatest mysteries in physics. Leading theories suggest it represents vacuum energy arising from quantum fluctuations in empty space. Alternative models propose that dark energy varies over time, or that gravity itself behaves differently at cosmic scales. Some theoretical calculations suggest that dark energy acceleration will continue increasing until it overcomes nuclear forces holding atomic nuclei together. This Big Rip scenario would tear apart galaxies, star systems, and eventually atoms themselves, approximately 22 billion years from now. But dark energy also creates opportunities for cosmic observation. The accelerating expansion allows astronomers to see farther back in cosmic time by observing galaxies at distances where recession velocities approach light speed. These observations reveal cosmic conditions when star formation rates exceeded current levels. Dark energy measurements also provide tests of Einstein's general relativity across cosmic scales. Precise observations of cosmic acceleration help determine whether gravity behaves as Einstein predicted or requires modifications at the largest observable distances. The discovery of dark energy fundamentally changed our understanding of cosmic composition. The universe consists primarily of components we cannot directly detect. Dark energy and dark matter together comprise 95% of cosmic contents. Normal matter represents only 5% of universal reality. Most galaxies visible in tonight's sky will vanish from human view within the next 2 trillion years. Dark energy acceleration will carry these cosmic neighbors beyond our observational horizon, leaving future astronomers with an almost empty night sky containing only galaxies within our local group. This cosmic isolation has already begun. Galaxies at distances exceeding 14 billion light-years currently recede faster than light speed due to cosmic expansion. Light leaving these distant systems can never reach Earth because space expands faster than photons can travel through it. We observe these galaxies only because their light began the journey toward us when they were much closer. Computer simulations reveal the timeline of cosmic loneliness. Within 50 billion years, the Virgo cluster will disappear beyond our cosmic horizon. The most distant galaxies we can currently observe will fade from view as their light becomes too redshifted to detect. Within 100 billion years, only local group galaxies will remain visible to observers in our cosmic neighborhood. But even this reduced galactic family faces internal changes. The approaching collision between our Milky Way and Andromeda will reshape the local group within 5 billion years. Smaller galaxies will be disrupted or absorbed during this merger, reducing the number of distinct galactic systems in our immediate vicinity. Future astronomers living in the merged Milky galaxy will inhabit a profoundly different cosmic environment. Their night sky will contain no external galaxies beyond their local merged system. Deep space will appear empty except for the cosmic microwave background radiation, which itself will become too faint to detect as cosmic expansion stretches its wavelengths beyond instrumental sensitivity. This cosmic isolation creates a disturbing possibility for future science. Astronomers living billions of years from now may have no evidence that other galaxies ever existed. The expansion history of the universe will be erased from observational records. The Big Bang Theory might never be discovered because the evidence supporting it will have disappeared beyond detection limits. Yet current observations suggest that cosmic acceleration may increase over time. If dark energy density grows as some theoretical models predict, the expansion rate could accelerate until it overcomes gravitational forces within individual galaxies. Stars would be torn away from galactic centers, planetary systems would be disrupted. Eventually, even atomic nuclei could be ripped apart. This scenario, called the Big Rip, represents the ultimate triumph of dark energy over all other forces in nature. It would occur approximately 22 billion years from now if current acceleration trends continue increasing. The universe would end not in heat death, but in a cosmic explosion that tears apart every bound structure. But less extreme models suggest that dark energy might remain constant or even decrease over cosmic time. These possibilities would prevent the Big Rip while still isolating distant galaxies beyond observational reach. The discovery of cosmic acceleration fundamentally changed our understanding of universal fate. Instead of eventually collapsing back toward a big crunch, the universe appears destined for eternal expansion and increasing isolation. We live during a golden age of cosmic visibility that will never return. Earth occupies the exact center of the observable universe. This statement appears to place humanity in a special cosmic position, reminiscent of ancient geocentric beliefs. Yet, this central location results not from cosmic design, but from the fundamental physics of observation and light travel time. Every observer in the universe sits at the center of their own observable sphere. The observable universe is defined as the region from which light has had time to reach a specific location since cosmic time began. This creates a personal cosmic horizon centered on each observer's position, making every location the center of its own visible cosmos. Alien astronomers in distant galaxies observe their own unique observable volumes that overlap with ours in some regions while extending into space we can never see. From their perspective, they occupy the center of the observable universe, while Earth lies near the edge of their cosmic horizon. This observational effect results from the finite speed of light combined with the finite age of cosmic time. Light from distant objects requires billions of years to reach any observer, creating a natural boundary beyond which nothing can be detected. This boundary forms a sphere around each observer because light travels at constant speed in all directions. The distance to our cosmic horizon measures 46.5 billion light-years in every direction due to cosmic expansion during light travel time. Objects that emitted light shortly after the Big Bang have been carried to this distance by expanding space while their ancient photons traveled toward Earth. But our central position comes with profound limitations. We can observe only a tiny fraction of total cosmic volume, with most of the universe lying forever beyond our detection. Our central location within the observable sphere provides no special access to cosmic secrets or privileged information about universal contents. The observable universe also changes continuously, as light from increasingly distant regions reaches Earth for the first time. Our cosmic horizon expands by 1 light second every second, gradually revealing new cosmic territory. Yet cosmic expansion simultaneously carries other regions beyond our permanent observational reach. This dynamic boundary means that the observable universe represents a moving window through cosmic space and time. We observe distant galaxies as they existed billions of years ago, while nearby objects appear in relatively recent configurations. Every cosmic observation involves looking backward through time across varying distances. Our central position also determines what physics we can study directly. Physical laws must be inferred from observations within our limited cosmic volume. Regions beyond our horizon might operate under different physical constants or alternative rules that we cannot detect. The cosmic microwave background provides our most distant observable boundary, representing the surface from which ancient light first traveled freely through space. This radiation wall surrounds us at maximum observational distance, marking the edge of everything we can potentially see using electromagnetic radiation. Beyond this wall lies a universe we know exists, but can never observe directly. Our central position within the observable cosmos grants us no special cosmic significance beyond the accident of our particular location. The Hubble volume represents the maximum sphere of space that Earth could theoretically influence through any physical process. This cosmic domain measures approximately 14 billion light-years in radius, encompassing every region where signals sent from Earth could potentially arrive before cosmic expansion carries them permanently beyond reach. Within the Hubble sphere, space expands at exactly the speed of light relative to Earth's position. Regions closer than this distance recede slower than light speed, allowing signals from Earth to eventually overtake the expansion and reach their destinations. Beyond the Hubble distance, space expands faster than light, making communication impossible regardless of the signal strength or transmission method. Confirmed calculations show that radio signals sent from Earth today could theoretically reach any galaxy within the current Hubble volume, though journey times would span billions of years for the most distant targets. These signals would arrive severely weakened by cosmic expansion and the inverse square law governing electromagnetic radiation. But the Hubble sphere shrinks continuously as dark energy acceleration increases cosmic expansion rates. Galaxies, currently within Earth's sphere of influence, cross beyond the Hubble distance at an accelerating pace. Each day, cosmic regions equivalent to millions of Earth-sized volumes pass permanently beyond our ability to influence through any physical mechanism. This shrinking sphere of influence creates a countdown for cosmic communication. Any messages Earth might send to distant galaxies must be transmitted before those targets cross beyond the Hubble distance. Once cosmic expansion carries them beyond this boundary, no signal from Earth can ever reach them, regardless of transmission power or duration. The concept of the Hubble volume also applies to receiving signals from distant sources. Galaxies beyond the Hubble distance cannot send signals that will ever reach Earth because space expands too rapidly for light to overcome cosmic recession velocities. We exist in permanent isolation from most cosmic regions. Current expansion rates suggest that the Hubble sphere contains roughly 10,000 times fewer galaxies than the observable universe. Most cosmic neighbors we can see today lie beyond our sphere of influence, meaning we can observe them but never communicate with them through any physical process. But the Hubble volume represents more than just a communication boundary. It defines the maximum region where Earth's gravitational field could theoretically influence distant matter. Beyond the Hubble distance, cosmic expansion overcomes any gravitational attraction between Earth and distant objects. This gravitational isolation means that most matter in the observable universe will never interact with Earth through any physical force. The galaxies we observe beyond the Hubble sphere might as well exist in separate universes because no causal connection can ever form between them and our location. Advanced civilizations within our galaxy could theoretically coordinate to send more powerful signals toward distant targets. But even these enhanced transmissions face the same fundamental barrier imposed by accelerating cosmic expansion. The Hubble volume also determines the maximum region where Earth's existence could potentially influence cosmic evolution. Beyond this sphere, the universe evolves independently of any actions taken within our cosmic neighborhood. Most of the cosmos remains forever beyond human influence or interaction. Beyond our cosmic horizon may lie infinite numbers of parallel universes, each containing different versions of reality where alternative histories unfold according to quantum possibilities. This multiverse hypothesis emerges naturally from cosmic inflation theory and quantum mechanics, suggesting that our observable universe represents just one bubble within an infinite cosmic structure. Eternal inflation models propose that new space constantly forms through quantum fluctuations in the cosmic vacuum. These fluctuations create bubble universes that expand into separate cosmic domains, each potentially developing different physical laws and containing unique arrangements of matter and energy. If eternal inflation proves correct, then every possible quantum outcome occurs somewhere within the infinite multiverse structure. Alternative versions of Earth exist where different evolutionary paths led to variations in history, biology, and human development. Some parallel Earths might harbor dinosaurs that never went extinct. Others might contain civilizations far more advanced than human society. The mathematics of infinite space suggests even more extreme possibilities. In an infinite multiverse, every possible arrangement of atoms must occur somewhere, including perfect duplicates of our observable universe repeated throughout cosmic space. Identical copies of Earth, containing precise duplicates of every human being, would exist in numbers approaching infinity. But these parallel worlds remain forever inaccessible from our cosmic domain. The expansion rate between different inflation bubbles exceeds light speed by enormous factors, preventing any communication or travel between separate universe regions. Each bubble evolves in complete isolation from its parallel neighbors. Some quantum interpretations propose that parallel universes form every time quantum systems make probabilistic choices. Each possible outcome branches into a separate timeline, creating infinite numbers of parallel realities where every conceivable version of history occurs simultaneously. These quantum parallel worlds might exist in higher dimensional spaces that intersect with our three-dimensional reality only at quantum scales. Advanced physics theories suggest that our familiar space represents a lower dimensional surface embedded within higher dimensional structures called branes. String theory models propose that multiple brane universes could exist within the same higher dimensional space, occasionally colliding to create what we observe as Big Bang events. Our universe might represent just one brane among countless others, floating through dimensions we cannot perceive directly. But parallel universe theories remain largely speculative because they make predictions that cannot be tested through direct observation. The evidence supporting multiverse models comes primarily from theoretical consistency rather than experimental confirmation. Recent observations of cosmic microwave background patterns might provide indirect evidence for parallel universes. Some theoretical models predict that collisions between bubble universes would leave detectable imprints in the radiation from our cosmic horizon. Advanced search algorithms analyze cosmic microwave background data for circular patterns that might indicate collision signatures from neighboring universe bubbles. Several candidate signals have been identified, though their interpretation remains controversial among cosmologists. The discovery of parallel universes would fundamentally change human understanding of existence and significance. Every possible version of reality would exist somewhere within the infinite multiverse structure. Our observable universe, containing 2 trillion galaxies and more stars than sand grains on Earth, might represent an infinitesimally small component of total cosmic reality. Theoretical physics suggests that our entire observable universe, containing 2 trillion galaxies across 93 billion light-years, might be smaller than a subatomic particle within a vastly larger cosmic structure. This mind-shattering possibility emerges from models proposing infinite hierarchies of organization, extending far beyond anything humans can observe or imagine. String theory and quantum gravity models suggest that space-time itself may be quantized at the smallest scales, consisting of discrete units smaller than anything current physics can measure. If space truly consists of quantum pixels, then our observable universe might contain only a finite number of these fundamental space-time units. But infinity allows for structures of unlimited complexity within any finite volume. Mathematical models propose that infinite amounts of information could be encoded within arbitrarily small regions of space-time through fractal organization or higher dimensional compression techniques. These possibilities suggest that our cosmic horizon might represent just one level in an infinite hierarchy of nested realities. Structures within our observable universe might contain entire cosmos of their own, while our universe might exist as a component within incomprehensibly larger organizations. Advanced civilizations within our galaxy might possess technologies capable of accessing information stored at quantum scales. Theoretical proposals suggest that enormous amounts of computational power could be packed into microscopic volumes through quantum processing techniques that exploit fundamental properties of space-time. But the infinite hierarchy concept extends beyond simple scaling relationships. Each level of organization might operate according to different physical laws or mathematical principles. The physics governing our cosmic scale might break down completely at larger hierarchical levels. Some theoretical models propose that consciousness itself might exist at multiple hierarchical scales simultaneously. Human awareness might represent a low-level phenomenon within vast cosmic intelligences that think thoughts lasting millions of years while processing information across galactic distances. Conversely, the neural activity within human brains might contain conscious entities existing at shorter timescales, experiencing entire lifetimes within what we perceive as single thoughts. Each level of consciousness might remain unaware of the others, despite sharing the same physical substrate. The infinite hierarchy hypothesis also applies to mathematical reality itself. Our physical universe might exist within a mathematical structure that represents just one component of an infinite library containing every possible mathematical system. This mathematical multiverse would include universes governed by alternative geometries, different numbers of dimensions, or completely alien logical systems. Physical reality might emerge from mathematics rather than mathematics describing physical reality. Recent advances in computational science have revealed that simple mathematical rules can generate infinite complexity through recursive processes. Mandelbrot sets and cellular automata demonstrate how basic algorithms can create structures containing unlimited detail at every scale of magnification. If reality follows similar principles, then the complexity we observe throughout our cosmic neighborhood might represent just the surface layer of infinite organizational depth, extending both inward and outward from human scales. The discovery of infinite hierarchical organization would render human significance simultaneously infinitesimal and infinite. We would exist as microscopic components within vast cosmic structures, while potentially containing entire universes within our own physical processes. Every scale of existence might harbor forms of organization and consciousness beyond current human comprehension. Imagine shrinking our entire observable universe until it becomes smaller than a single atom within a larger cosmic structure. This scaling exercise reveals just how insignificant our cosmic neighborhood might be compared to the true extent of existence beyond our furthest observational horizon. An atom measures approximately 1/10,000,000th of a meter across. If our observable universe, spanning 93 billion light-years, compressed to atomic size, the larger cosmos containing it would measure incomprehensible distances. The ratio between our universe and this hypothetical larger structure would exceed the ratio between an atom and our observable cosmic volume. Theoretical models suggest this scaling relationship might actually represent physical reality. Eternal inflation creates infinite amounts of space containing unlimited numbers of observable universe-sized regions. Each region would appear microscopic when viewed from the perspective of the infinite cosmic structure containing them all. But the scaling possibilities extend even further. If infinite hierarchies of organization exist, then the larger structure containing our universe might itself be smaller than an atom within an even vaster cosmos. This recursive scaling could continue infinitely, making our observable universe infinitesimally small compared to ultimate reality. Advanced physics theories propose that information content, rather than physical size, determines the significance of cosmic structures. Our observable universe contains approximately 10 to the 120 bits of information encoded in the positions and properties of all particles within cosmic space. This information content might represent the true measure of our cosmic significance, rather than spatial extent. Even if our universe appears microscopic within larger structures, it could contain unique information patterns that make it valuable or interesting to cosmic intelligences operating at larger scales. Some theoretical models suggest that conscious observers might exist at multiple scales simultaneously. Vast cosmic minds might think thoughts that encompass our entire observable universe while remaining unaware of the detailed processes occurring within human-scale consciousness. Conversely, quantum-scale processes within human brains might harbor conscious entities experiencing complex lifetimes within what we perceive as brief neural events. Each level of consciousness might operate according to different timescales, while sharing the same underlying physical reality. The possibility that our universe exists as a subatomic component within larger structures challenges traditional concepts of cosmic importance. Every human achievement, every stellar explosion, every galactic collision might represent microscopic fluctuations within incomprehensibly larger cosmic processes. Yet this scaling relationship could also suggest that unlimited complexity exists within structures we consider small. If our universe can be compressed to atomic scale while retaining its full information content, then individual atoms in our world might contain cosmic structures of their own. This fractal organization would mean that complexity exists at every possible scale, without fundamental upper or lower limits. Zooming outward or inward would reveal new levels of organization, extending infinitely in both directions. Recent discoveries in quantum mechanics suggest that empty space contains virtual particles that constantly appear and disappear at subatomic scales. These quantum fluctuations might represent shadows of cosmic processes occurring within the underlying structure of space-time itself. Our entire cosmic neighborhood might be nothing more than foam on an infinite ocean of existence. You are reading these words on one planet, orbiting one star in one galaxy, among 2 trillion cosmic neighbors, scattered throughout an observable universe that might be smaller than an atom in ultimate reality. This perspective places human existence within a context so vast, it challenges every assumption about significance, purpose, and cosmic importance. Earth measures roughly 25,000 miles around, a tiny rock spinning through space at 67,000 miles per hour around a nuclear furnace that consumes 4 million tons of matter every second. Our Sun ranks as a perfectly average star among 400 billion stellar furnaces populating our galactic neighborhood. The Milky Way galaxy spans 100,000 light-years, while containing enough stellar material to power quadrillions of civilizations. Yet our entire galactic home represents just 1 grain of sand on an infinite cosmic beach, containing more galaxies than grains of sand on every beach on Earth. Each of these 2 trillion galaxies harbors billions of stars, many hosting planetary systems where conditions might support life. Conservative estimates suggest that hundreds of billions of Earth-like worlds exist within our observable cosmic volume. Some of these planets likely developed civilizations millions of years before human society emerged. Yet the observable universe itself may represent less than 1% of total cosmic reality. Hidden beyond our cosmic horizon lies a universe potentially extending infinitely in all directions, containing infinite numbers of galaxies, stars, planets, and possible civilizations. Parallel universes might exist where different versions of history unfold according to alternative quantum possibilities. Infinite cosmic hierarchies might contain our entire observable universe as a microscopic component within incomprehensibly larger structures. This cosmic perspective simultaneously renders human existence infinitesimally small and profoundly meaningful. We represent temporary patterns of organized matter that achieved the remarkable ability to contemplate cosmic scales far beyond our evolutionary origins. Humanity developed from simple chemical processes on one small planet, yet we have discovered cosmic structures spanning billions of light years. We evolved to hunt and gather on African plains, yet we have mapped the large-scale structure of the universe and detected gravitational waves from colliding black holes. The same cosmic processes that created galaxies, stars, and planets also created the complex chemistry that led to biological evolution and human consciousness. We are literally made of star stuff, forged in nuclear furnaces and scattered through space by stellar explosions. Every atom in your body, except hydrogen, was created inside a star that lived and died before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all came from stellar nucleosynthesis, occurring billions of years ago in cosmic neighborhoods far from Earth. This material connection links humanity to cosmic evolution across space and time. We represent the universe becoming aware of itself, matter achieving consciousness, and developing the ability to study its own cosmic origins. Despite occupying one tiny corner of an infinite cosmos, humans have discovered fundamental truths about reality that apply across cosmic scales. We have glimpsed the true size of existence. The universe is not only stranger than we imagine, it is stranger than we can imagine, and we are here to witness it all.